Good morning and welcome back for the third day of the lecture. And I think we should briefly repeat what we have learned yesterday about algebras, and then we continue with the slides for today. So let me just repeat this basic concept that a vector space can be made an algebra by introducing a product on that space, fulfilling the obvious axioms of associativity and distributivity, and then a vector space turns into an algebra. We have said that an algebra should be called commutative if any elements commute with each other. We say that an algebra is unital if it contains a unit, so a neutral element regarding the multiplication. And then we have seen that if we not only have a vector space, but if we have a Banach space, which is a norm-completed space where every Cauchy sequence takes its limit, then we can generalize this towards the notion of the Banach algebra, where we have additionally to claim that there should be also an axiom describing how the algebra product combines with the norm. And again, this norm induces a uniform topology on the space, on the algebra then, and we can describe convergence properties, we can compute power series and all that. And eventually, we introduce this mapping from the algebra into itself, which is called an involution if these axioms hold. You see already this has some resemblance with complex conjugation in the complex number field, and therefore we try to preserve as much properties from the complex number field, putting all these structures into the algebra except commutation. Commutativity would be a special case, and we will immediately see how these properties relate to the different concepts that we have seen before. And finally, one introduces the so-called C-star property, which now relates all things together, the algebra product, the involution, and the norm together. And here you see again, this is quite common from the complex number field. So I gave you several examples. So first of all, the complex number field itself can be regarded as a commutative or abelian C-star algebra over the real numbers, of course, because the complex number field is isomorphic to the space R2. And eventually we define the modulus of a complex number exactly in that way. It's the square root of the complex conjugate times the number itself, and this is simply the C-star property. Then we have seen that we can discuss continuous function over some topological space. So for example, over the n-dimensional hypercube in a particular example, and this space of functions becomes a C-star algebra by employing all the well-known operations on functions that they can be pointwise added together. They can be multiplied pointwise with a scalar, and we have pointwise multiplication of these functions. In this particular example here, where we have a bounded phase space for the arguments, we can define the maximum norm, and complex conjugation is simply the involution is simply complex conjugation of the values of the functions. And I have already said that one first example in neuroscience could be the probability for a spiking neuron, which would be a real number between 0 and 1, and then we have a neural network, a network of n neurons, and therefore the corresponding phase space would be the n-dimensional hypercube, that example. I have said something about the topology here, because this maximum norm, or more generally the supremum norm that we can introduce for locally compact phase space that describes the uniform convergence of function series. So we are able to define essentially Taylor series exponential functions and everything like that in our C-star algebra. And another example now for a non-commutative C-star algebra was provided by what we have learned about pioneer quantum mechanics. Namely, we consider a Hilbert space. We take all the operators, linear operators, or linear homomorphisms on this Hilbert space. And now, in order to compute a norm of these operators, they must be the bounded operators. So the eigenvalues of these operators must be bounded, of course, and then we get the C-star algebra of the bounded linear operators over a Hilbert space as the example of a non-commutative C-star algebra. And here again, because we have a Hilbert space, which is a linear space which admits addition and scalar multiplication, we use these properties of the Hilbert space in order to define the corresponding properties in the algebra. So the sum of two operators is acting on a state is simply given as the sum of the outcomes of the reciting states after applying the operators, and the same for the scalar multiplication. And particularly different here is, of course, the product of two operators, which is given by the function composition of the corresponding mappings. And then we introduce the subprimum norm because we assume that these vectors remain bounded, and we can introduce the involution simply by replacing the operator with its conjugate, so to say, but applying it now to the left to an adjoint vector, to the dual vector from the dual space of the Hilbert space. I gave you another application for this, namely in pioneer quantum mechanics. All bounded linear operators are valid observables, and this is essentially one of the postulates or one of the axioms that John von Neumann has introduced in order to codify the mathematical properties of pioneer quantum mechanics. So this is called von Neumann's irreducibility postulate. And we shall come back to this issue somewhat later, because what I have already mentioned yesterday is assuming this irreducibility postulate prevents us from discussing classical properties of such a system. There are no classical properties. So then we can continue today. We make some definitions about properties of elements in such a C-star algebra. And I have already mentioned that one should clearly distinguish between the properties of the elements when they are considered as operators on a Hilbert space and their algebraic properties alone. So here I would say that an element of the algebra is called Hermitian if it is simply the same as its adjoint. We call it unitary if the product of an element is its adjoint with the unit. And we call it idempotent if the square of the operator is the operator itself or is the element of the algebra itself. And if A is both together Hermitian and idempotent, we call it a projector. And please remember, looking at bounded operators on a Hilbert space, Hermitian is closely related to self-adjointness. So then one generally speaks about self-adjoint operators. Unitarity is closely related to isometry. I think I can just make a small comment on that. What do we call and when do we speak about an isometry? When the scalar product remains invariant. So I have introduced at the very beginning the scalar product as this sesquilinear function here. So we can write it in that way. This is the scalar product of two elements of the Hilbert space, x and y. And we claim that should be invariant when we apply the operator in Hilbert space on both arguments. And then we say this operator should be an isometry. But now, of course, because we have a Hermitian cis-trilinear form, we can bring one of the operators into the other arguments, so that it's the same as U star Uy. And now, using this algebraic property of unitarity, we see that it's the same as X. The identity operator, or call it I again, and Y. And this is, of course, the same as X, Y. But here, of course, we have the same distinction to be made as for the self-adjoint operators. These values here, U applied to X and U applied to Y, they must exist, of course, as images in the Hilbert space. And therefore, it's always important to take the domains of these operators into account. And this makes a distinction, I would say, between the purely algebraic properties that we have here and the properties of these operators when they are acting on a Hilbert space, where we always have to take the domains into account. Well, here's another example again, looking again at the commutative C-star algebra of the continuous complex valued functions over some compact Hausdorff space and some topological space, which we call the phase space in general, which can be considered as n-dimensional hypercube. And now we are asking which functions, so we are looking for continuous complex functions, complex valued functions. Which of these functions have the property being idempotent and, of course, Hermitian? So they should take only real values in order to be Hermitian in this example here. And what do we have to claim to have the property of idempotence? And then, of course, the square must be the same as the original value. And this holds only because we are working in a number field. Only the numbers 0 and 1 have this property. 0 to the power of 2 is 0, and 1 to the power of 2 is 1. But of course, these are functions, and so we introduce two functions, namely the null function, one can say, which is 0 for all elements on the hypercube, and the other function, which is 1 for all elements on the hypercube. Interestingly, here you see this is a very important issue in algebraic quantum theory. If we relax this assumption here, that our phase space should not be bounded anymore, would we still have this projector in the algebra? And the answer is not. Because, of course, this is the identity function is a continuous function, but only regarding this bounded set of arguments. And if we allow for example, for the entire R2n, this function is not bounded anymore, and therefore it must be excluded from the function space. It does not have a definite norm, and therefore this projector here does not exist in an algebra. I have again some problems here. Does not exist in an algebra when the phase space is not bounded or is not compact anymore. So for a locally compact Hausdorff space, we only have this projector left, and this is quite a general property. And we see star algebras have in general only a very little number of projectors. Here, for example, you can identify these both projectors. In the case of a locally compact but not compact phase space, we have to get rid of this one because it does not belong to the algebra of complex valued continuous complex valued function. This is quite interesting, and we come back to this issue much later. But here you see this is really an interesting property of C-star algebras, that purely algebraic things, purely algebraic properties are closely related to topological properties. If we relax, so here we have a compact phase space. If we relax this, and in this compact phase space, we have this projector. So that is a unitary algebra. And if we if we relax this property, if we say the phase space should not be compact anymore, but only locally compact, we don't have this projector anymore. And the algebra is not unitary, is not unitary anymore. So in C-star algebra, you see a very close connection between algebraic properties and topological properties here in this case. Well, now we come to a very important concept, which is called the commutator. And here from the very definition, you already see that a commutator of an algebra is, so to say, a measure of commutativity, or one can say a measure of compatibility, because in the discussion of pioneer quantum mechanics, we have seen that two observables are called compatible if they are algebraically commuting with each other. And then you see just bring one of the terms to the other side. That means that the commutator of the two elements A and B is vanishing. So the commutator is a very instructive tool for discussing the degree of commutativity of such an algebra. And yeah,
sorry, just from my understanding in the previous slide.
The previous slide, yes.
The 0 and the 1 are, of course, the 0 and 1 vector.
No, these are numbers. So these are vectors. These are the arguments are vectors in this topological space. But the algebra is the algebra of complex valued functions.
Okay.
Because we have only to take the Hermitian elements into account, we are dealing with the real valued functions.
Okay.
Yeah.
Yeah, I was still on the operators. Okay.
Yeah.
Thank you.
Because here we don't have to talk about operators. This is simply a function space.
Okay.
So to say a scalar field, one can say. This is a scalar field over this vector space here. Okay, and then of course we can derive several properties. So the first rule, of course, if you insert A and A here, you immediately get this 0. Then, of course, you see the commutator changes its signs by exchanging the arguments. This is also clear from the definition. It's easy to prove also that we have these two laws of distributivity for the commutator. And then there's this final identity, which indicates that the commutator has the nice property being a derivative. So the commutator allows us to define just algebraically the derivative of elements. And perhaps we can try to prove that last line here. So it means ABC should be evaluated. This is actually ABC minus CAB. So what can we do now? Do you see any similarity? I think we have to add and then also to subtract another term. Can you see that? What we have to do? So perhaps we...
Plus ACB minus ACB.
What?
Plus ACB minus ACB.
ACB, oh, sorry. Let's try. Then we have A. And this was this part, and now we have this part plus A. Maybe I will need another line. in order not to get confused. C, A, B. This is already the commutator. And here we can bring B to the other side, and then we have A, B, AC minus CA times B. Right. Exactly. Yeah, so these are the essential properties of the commutator. I think, by the way, this is called the Jacobi identity in calculus. So, yeah, I think so. And now we make one preliminary assumption. We simply assume that our C-star algebra is generated by a countable basis of elements. So as considered as a vector space, it should be the set of all linear combinations that can be formally created from these basis elements here. And then we can compute all the possible commutators. And if all these possible commutators have this exactly this relation, that the commutator of the element AI and AJ is just a linear combination of all the other elements, of course, because we are talking about a basis here, it should be possible to express this as a linear combination. And the coefficients appearing in this linear combination. So we are summing over K, and then of course we have to fix the indices A and I and J. And these are called the fundamental commutation relations. And so we have a parameter assignment here that all the indexed triples are mapped to some complex coefficients. They are called the structure constants of the algebra. So this is really the core, so to say, of the algebraic point of view, that all the structural properties and therefore all the properties that can be derived, topological properties, everything like that, this is all encoded in these fundamental commutation relations. And now I would like to present you some examples, and we have already discussed this example in our in the part of the quantum computing part of the lecture. So we can consider the so-called Pauline spin algebra. This is an algebra that is generated by the three elements, namely measuring spin in x directions, measuring spin in y direction, measuring spin in z direction. And we have to take the linear combinations with real elements here in order to give them a physical meaning. And this algebra is called SU2. Do you know why it's called SU2? Because that's
Special unitary algebra.
precisely. This is a special unitary algebra in 2 dimensions. And this is related to the Lie group of the special unitary operations in 2 dimensions. So this is also closely related to some symmetry that can be studied in quantum systems. And of course, the most obvious symmetry is exactly what we have discussed about qubits or spins. And here are the fundamental commutation relations. They show that the commutator of Sx and Sy is simply I times Sz. Sy and Sz is I times Sx. And you see it depends on cyclic permutations of these arguments. Of course, you can also compute the commutators of Sx and Sx, and then you get simply 0. This is clear. I haven't provided these examples because they are trivial. So the structure constants in this representation here are simply 0, I, and minus I. This is the Pauline spin algebra, what we have discussed already before. Here's another interesting algebra, which is called the Heisenberg algebra. Here you see it's a unitary algebra because it contains the identity. Interestingly, the Pauli algebra does not contain the identity. But of course, as I have already mentioned, an identity can always be adjoined to an algebra. So for the spin algebra, one can make a formal construction that gives you the so-called universal envelope, and then you are embedding the spin algebra into a larger algebra which contains the unity or identity. So, and here we have the identity, and we have two operators which have their physical interpretation as the momentum operator and the position operator. And of course, both operators commute with identity. And then here is the crucial Heisenberg commutation relation. The commutator of position and momentum is I times the identity. Of course, in physics, one has to include here Planck's constant of action as well. But we can gauge a unit system in such a way that the constant of action is simply 1. This is done quite often, so in mathematical physics. And you see the structure constants are exactly the same as the Pauline algebra. And you can also formally relate both algebras together, so there's not so big difference between them. So this is the Heisenberg algebra. Of course, going back to Werner Heisenberg in his first attempt to formalize the physical ideas of quantum physics in terms of his matrix mechanics. And here is another representation or another algebra. It's called the Weil algebra. And this deserves quite some further consideration. So first of all, what is written there? So the general element of the Weil algebra is given in that way. So now we have here two parameters, P and Q. And I repeat this. This is E to I e to half, E to minus E to P, E to Q. And these parameters are members in R2. We will discuss their physical meaning immediately. And now you see the commutation relation in this algebra is written down in that way, so there is no commutator appearing anymore. And quite often, even for more complex algebraic systems, we don't have the possibility to express the commutation relations by means of commutators. Here we have such an example, and if you would take a closer look, you will see this is describing a unitary projective representation of this parameter space R2. So here, of course, neglecting this phase factor here, you see this is simply describing some kind of group representation. So W of P1, PQ, W P2, PQ is given by W of P1 plus P2, Q1 plus PQ. This is a kind of group homomorphism, and this is essentially including this phase vector here. This is called a unitary projective representation of this parameter group. But what is the physical meaning of this? So let us discuss two particular examples, namely, first of all, set P to 0 and look at only Q. If one of these both parameters is 0, this phase factor disappears, and this one disappears as well, and we only have minus IQ. P and Q are simply momentum operator and position operator of the Heisenberg algebra. So the Weil algebra is first of all just a reformulation of the Heisenberg algebra, but we will see immediately what this means. Okay, this is an exponential of the position operator appearing, of the momentum operator, appearing in the Heisenberg algebra. And the point is now, these operators in the Heisenberg algebra, they are self-adjoint when they are acting on a Hilbert space. What is the result of computing the exponential function of a self-adjoint operator? It's unitary, precisely. And unitary operators in quantum physics express symmetries, symmetry transformations. And we have to look for the corresponding symmetry transformations, but I will omit this for the other operator. Of course, you can equally compute this one, and then you see it only contains this expression here. But let us further look at this operator here. Of course, it is an exponential function taken from an operator argument and not from a number argument. So how can we express this operator? Of course, we have to write down the exponential series. And I have said to you that in these C algebras, we have almost all the properties that we know from real and complex analysis. So we can compute calculus, we have conversions of power series and so on. And what is the result? So we have to take this argument to the k, normalized by k faculty. And that's it, right? Let us look into more detail at this one. This is u to k over k faculty and k. What does this mean? So in order to understand the physical meaning of this expression, we have to apply this to a Schrödinger wave function, because Heisenberg algebra, you remember, they are applied to wave functions, and then we have to express the momentum operator as an operator, how it is acting on a wave function. And we had the slide somewhere before, or do you remember what was the particular form of the momentum operator?
Minus I partial derivative of respect to x of q. Minus I partial derivative.
Precisely, yes. Thank you very much. This is quite helpful, yes. So I don't have to go back all the slides. Precisely. And now we can continue this calculation here. To the power of k. So that means now we have minus I to k, minus I to k. What is this? This is just minus u to k. Am I right? Okay. And then here we have this operator to the power of k. And now let us apply this operator to a wave function. And I don't write this in the Dirac notation. I simply write it in the position representation. So this is our wave function on the configuration space. And this means I have to write down the series expansion. And then we get here simply the case derivative of the wave function. And what do we have now? Can you see?
The minus is something in the parentheses.
Minus minus, and then I
-1 to the k. No? -1 to the k. In the summation,
yes.
we have sum over k of -1 to minus q in parentheses k.
Okay. Sorry. Yes, you're right. Yes, of course. Yeah, this is a crucial point. So, but now I think you should be familiar with this expression. This is a Taylor series. This is the Taylor series of that. And so this is the physical meaning of this while operator. It describes translation in space. And so now, physically speaking, these while operators provide not an algebra, but first of all, they provide a group, namely the group of space translations. And we can see that the second operator here that turns out from this parameter choice, this describes Galileo relativistic transformation of momentum. So what is called a boost of velocity. And first of all, these operators have a group structure. This becomes clear also from this group property here from the commutation relation. And first of all, one is speaking about the while group, because physically, the while group is just a group of space translations and velocity boosts. But then, from a formal point of view, mathematical physicists have generalized this idea that you can take all the formal power series, all the formal polynomials of these both operators here, of all these parameterized operators here, and then you get the so-called while algebra. And this led to a breakthrough regarding the problem that here position and momentum operator are not bounded on the Hilbert space because they're exponentials, they are bounded operators now. And so, since the reformulation of the Heisenberg algebra in terms of the while algebra, these problems with infinite space have been solved. And you can argue that the while algebra is the proper algebra for describing the canonical commutation relations of Heisenberg. That's the point. So the physical meaning is the while group, the group generated by space translations and velocity boosts, and its generalization. So the group algebra that is generated by all the formal power series, all the formal polynomials of these operators is the ground, so to say, for discussing Heisenberg's commutation relations in the framework of algebraic quantum theory. But now I would like to make another comment. What is the parameter space here? Well, we have seen that Q corresponds to a space translation, and correspondingly P corresponds to a velocity boost. So this parameter space is nothing else than the phase space of a classical system. And so here we see also in the framework of mathematical physics how the algebraic approach merges quantum approaches and quantum aspects and the mathematics of classical physics together. The while algebra is parameterized by the phase space of a classical system. And here, of course, we have discussed a system with only one degree of freedom. So we have a one-dimensional configuration space. The particle is, so to say, still the particle in a box, which is only to move along one direction. And then we have a two-dimensional phase space, and this is the parameter space of the Weil algebra. That's it. Here's another important example, namely now from quantum field theory, and this is called the field algebra. And here you see a crucial difference also to the Weil algebra. So in the examples before, when we have introduced the structure constants, we had a countable basis of algebra elements. In the case of the Weil algebra, we have a continuous representation, namely a continuous parameter space, basically the phase space of a classical system. But now, in order to consider quantum fields, we introduced this so-called field algebra. And this field algebra is, again, formally the set of all polynomials that can be generated by linear combinations and by products of these two operators here, or these two, I would say, I should avoid the term operator because an operator is always acting on a Hilbert space, but now we are in the algebraic framework. So these are two elements, and you see they are parameterized by states in a Hilbert space. And the interpretation will become clear when I shall repeat the application, or when I shall focus on an application of this field algebra. But here you already see that we are looking at the Hilbert space of a single particle. And in order to describe a quantum field, we should be able to generate many replicas of this single particle. And each of the replica could be in a different state in the corresponding Hilbert space. And this is actually achieved by these field operators here. And finally, one will see that this is a so-called creation operator, namely creating a state, creating a particle in this Hilbert space, state A. And this is the operator destroying a particle in this space. And of course, now we can also derive the commutation relations. These are the standard commutators we have seen. So the two annihilators, this is their interpretation, commute each other. The two creators commute each other. And if we compute the commutator of an annihilator and a creator, we get the identity multiplied by simply the scalar product of these two states in the Hilbert space.
Peter, can I ask you a question? Where is the notion of the replicas of the?
It's not clear yet. I will come back to this issue later. So first, because didactically, I decided to first explain the algebraic structure, and then in the applications, I will come back to the physical meaning. So, because we have commutators here, this is the field algebra of so-called Bose fields. So, like photons, like light. Bosons are particles that can be accumulated in a particular state. This is allowed by taking these commutators here. And of course, we can compute, or we can write down a field algebra for the so-called fermions as well. And the only thing that we have to change is then that we have to replace the commutators by the so-called anti-commutators. And an anti-commutator is simply expressing AB would not be the same as BA, but minus BA. So then, but we say that the two observables A and B do not commute, but they anti-commute. And that means that A, B, and here we include a plus index, assigning or indicating that we are expressing this term here. This is called the anti-commutator. And here again, you see that the fundamental commutation relations cannot be uniquely expressed by commutators alone. Here, in the case of fermions, we have to take these anti-commutators into account. So, but now the crucial difference to all the examples that we have discussed before, for a free particle or for a particle in the box, the Hilbert space is an infinite dimensional vector space. And so now our algebra is parameterized by these objects of the single particle Hilbert space. And that means we have a system with an infinite number of degrees of freedom. And this is really the crucial difference. I will come back to this point many times during the lecture, that here we see how the algebraic pictures really allows the treatment, the formal treatment of such objects, in contrast to everything that is known from the pioneer quantum mechanics, where we got all these peculiarities with respect to infinite dimensional number of degrees of freedom. Wait, and now I would like to make this point, this distinction between ontology and epistemology again, and the crucial point that I have learned here is that exactly these fundamental commutation relations of a C-star algebra, they uniquely describe what can be called the ontological structure of the system that we are investigating. So, and that makes it so important to distinguish between epistemology and ontology. We have an ontological description given by the algebra itself and by the fundamental commutation relations within this algebra, and they, so to say, describe the structure of the world as it is, independent from our observations, independent from our description. Now we need some further mathematical definitions. And the first one is what is a subalgebra? And of course, any algebra is a vector space, and you know that we can define a subvector space of a vector space, which is a vector space which is closed under the vector space operations, essentially closed under linear combinations. And similarly, we can define a subalgebra, a subvector space, call it U of a C-star algebra A is an algebraically closed, or is first algebraically closed with respect to the algebra product and the linear combinations and so on. And secondly, we also claim that it should be topologically closed with respect to the uniform norm, and that's called a C-star subalgebra. And another important notion is that of an ideal. I think I have mentioned that yesterday as well. So a subalgebra that is invariant under the algebra product. So that means all elements of the ideal times all elements of the algebra should not leave the ideal, should not leave that subalgebra. And I have already provided an example of that yesterday. So when we compute the expectation value of a density matrix, you have seen the density matrix must be of trace class. And the observables are arbitrary elements, of course, the self-adjoint or the Hermitian elements of the algebra. But this product must, of course, be of trace class again. And this essentially means that the density matrices are elements of such an ideal, while the elements of the algebra are elements of the algebra. The density matrices are elements of an ideal, and all the trace class operators, by multiplying them with algebra elements, are still in the ideal of trace class operators. So another important concept is that of the center of an algebra. So all the elements of the algebra that commute with all other elements of the algebra. So formally, all the elements Z of the algebra for which the commutator with all other elements 0, they constitute a subalgebra which is called the center of the algebra. Here's another example again. So look at the Pauli algebra generated by the spin operators as x, as y, and as z again. So taking the real linear combinations again, which is a special unitary algebra of 2 dimensions. And within this algebra, of course, we can not only compute linear combinations, we can compute polynomials. And this particular polynomial here, reminding you to the law of Pythagoras, the theorem of Pythagoras, this is called a Casimir operator. And one can formally prove, I will not do this here, yet you can formally prove that this operator here belongs to the center of the algebra. It commutes every other element of the algebra. So, and these notions, they give rise to the following distinctions. So now we are able to classify our algebras. Namely, classical systems are exactly those systems that are described by commutative or by abelian C-star algebras. And because the center of the algebra is the set of all the elements that commute with all other elements of the algebras, these algebras must be identical to the center. There's nothing else than the center of this algebra. So any abelian algebra, any commutative algebra is simply its own center. And this is the definition of a classical system in the algebraic framework. Proper quantum systems have a trivial center only, namely, of course, the zero operator commutes with all the other operators. And if the algebra is unital, or if the identity operator is contained in the center. So, of course, every such algebra has its center, but the center is called trivial. And a proper quantum system only has this trivial center. And finally, there are systems which have a non-trivial center, and these systems have the interesting property that they possess classical and quantum properties simultaneously. And at the end, I will show you that we can describe these more interesting systems in the algebraic framework.
Just out of curiosity, are there systems that combine both in reality?
Yeah, in reality. Yes.
Example?
Example is thermodynamic systems. So when you're looking at quantum statistical mechanics, of course, you have quantum observables like position and momentum of all the particles in the system, in the container also. And then you can show, because formally such a system must be described by those field algebras that I have explained before, which are algebras with an infinite dimensional parameter space. And then you can show that in such a system, classical properties emerge, and one of them is temperature, for example. The property of temperature is not reducible to quantum statistics, but it is emergent in an appropriate framework as a classical observable. Well, in order to make the next steps, I go back to my motivating example. So let us again look at such a classical dynamical system that lives in a phase space. So, for example, what you have seen before for the Weil algebra, where a particle with 1 degree of freedom has such 2-dimensional phase space. We have seen another example, which was the spring pendulum. And in this phase space, we can identify what is called a microstate in the classical system, which is the state the system has independent of any observation or so. And now, how do we describe an observable in a classical system? Well, an observable is formally nothing else than a mapping from the phase space to the real numbers, because all the observables must be real valued. And so we simply have this mapping from the phase space to the real numbers. And this leads to the following definition of an observable in the algebraic framework, namely the Hermitian, that means essentially the real valued elements of such a commutative function algebra of the continuous function over a topological space, which is equivalent to the phase space here of a classical dynamic system, where we can assume that the phase space is this bounded n-dimensional hypercube. These functions are called the classical observables. And so it's quite easy to say what will be the measurement result of the system in a given state, which is simply the value that the observable takes in this vector of the phase space. And this is a real number. This is the measurement result of the classical observable. And here again, you see, we are looking at function algebras abstractly, which are defined over a topological space, and then we can identify this topological space as the phase space of a classical dynamical system. And here again, one application in home neuroscience again. I have already mentioned that we can describe the activity of a single neuron by its probability to emit a spike or not. And if we do this for a network of n neurons, we have exactly the n-dimensional hypercube here again. And now we introduce a set of observables. And most straightforwardly, of course, you can describe an observable pi, mapping the phase space, the n-dimensional hypercube, to the unit interval of spiking probabilities. Simply by projecting this high-dimensional state vector towards one of its coordinate axes. And this gives us the observable to observe the neuron number I within the neural network with this particular spike probability. So here you see how all these concepts really can be straightforwardly applied within the algebraic frame.
Sorry, in this
Yeah.
What will be?
What?
So in this case, the microstate is just the activation value of 1 neuron.
No, the microstate of the system is the activation vector of the entire network.
Yeah.
The instantaneous activation. And now you are introducing the observables. The algebra of observables is, so to say, generated by these projectors, projecting the state vector of the entire network onto all the individual coordinate axes, and then you get the activation of all these particular numbers.
So observable will be the state of 1 neuron, for example.
Yeah. Well, now we can again discuss the case for quantum systems, where we have looked at this Stern-Gerlach experiment. So we have a beam of silver atoms that pass such an inhomogeneous magnetic field, and then we have experimentally observed that the beam splits up into downstream and an upstream. And so in the downstream, we observe spins with spin down orientation, and upstream, we observe the spins with spin up orientation. And this is mathematically described by this single observable as Z, measuring spin orientation in Z direction. So, work. Okay, this works. And now again, and this is nothing new for you because we have already defined observables in the Hilbert space framework, but now it's the same in the algebraic framework. Just the Hermitian elements of this non-commutative algebra of bounded linear operators in Hilbert space for the quantum system. These are called observables, also in the algebraic picture. And so there we simply export exactly the same notion that we have learned before. And now the value of the observable in some state, some pure state of the Hilbert space is then simply given as the eigenvalue of the corresponding eigenvalue equation. So this relates again how the observables, which act here on state vectors in the Hilbert space, are related to the measurement size. Another important concept would be then the notion of intrinsic properties. So we have seen that we can define a subalgebra within a C-star algebra, and we can say whether a subalgebra should be maximal if it does not contain any other proper subalgebra, and we can identify abelian or commutative subalgebras. And sometimes we have the situation that we can identify one or more maximal abelian subalgebras of the Hermitian elements in the C-star algebra. And the elements of such a maximal abelian subalgebra, they are called the intrinsic properties. And what does this mean? Because we are dealing with a abelian subalgebra, that means all the intrinsic properties can be simultaneously measured precisely. Not only with some dispersion, but they have precise values. And this relates back to our discussion about the lattice structure, because then one can see that such maximal abelian subalgebras correspond precisely to the Boolean blocks of the corresponding projector lattice. We have seen in general for quantum systems, the lattices are not Boolean lattices because they are not distributive, but they are in general orthomodular lattices, and these orthomodular lattices have a particular structure that we can identify Boolean blocks. And these Boolean blocks describe different perspectives. You remember this Chinese lantern lattice from the first lecture. And these Boolean blocks correspond exactly to these maximal abelian subalgebras of intrinsic properties. Exactly intrinsic properties are simultaneously actualized and can be precisely measured. That means without dispersion in the corresponding states. And here's again one example. Looking at the spin algebra again, we have seen that the Casimir operator belongs to the center of the algebra, and now therefore the Casimir operator commutes with all the other generators of the algebra, and then we can take, for example, the Casimir and Sx, or the Casimir and Sy, or the Casimir and Z, and these are maximal abelian subalgebras. In physics, usually one makes the choice to decide for this Boolean description, so to say, and then all the other properties can be derived from that.
Peter,
yeah.
Sorry, can you go back to this slide? I think something skipped from my mind. So if you go back to the slide on observable in quantum system, I think it's just here. Something escaped me. So how did you solve the irreducibility postulate by von Neumann? How did we solve in this algebraic framework the irreducibility postulate by von Neumann? Something this idea that irreducibility postulate by von Neumann.
It's not addressed here.
No, it's not addressed here, but how did we, in this algebraic framework, we solve this problem here?
Oh, I'll come back to this later.
Okay.
It will be another example.
Okay.
Yeah. So, but this is not an issue here at the current stage. So now we have seen that we can identify these maximal abelian subalgebras. And in fact, in physics, when we are looking at such spin systems and applying these elements to a Hilbert space, we can identify all the basis functions of the Hilbert space as by the corresponding eigenvalues of the Casimir and of one of these operators. And usually one uses the eigenvalue of the Casimir, which is, so to say, the magnitude of the angular momentum, and the eigenvalue of the SZ operator simply gives the projector of the angular momentum onto the z-axis, and these two values are able to characterize the corresponding basis set within the Hilbert space. And by the way, another example would be, for example, when you solve the Schrödinger equation for a particular problem, for a hydrogen atom, for example, you see that it is possible to precisely measure 4 properties of an electron in a hydrogen atom. And this is energy, it is angular momentum, namely the magnitude of the angular momentum. It is one projection of the angular momentum, and of course spin. And these 4 properties are intrinsic properties. They have sharp values for the electron in the hydrogen atom, and therefore serve as a characterization of all the eigenstates that you can derive there. And of course, these are essentially the 4 important quantum numbers, namely main quantum number is eigenvalue, or is related to the eigenvalue of the energy. Angular magnitude of angular momentum is related to what is called now I only have the German word available. Symbolically, you are distinguishing the quantum numbers N, M, L, S, Z. And these quantum numbers describe the state of an electron in the hydrogen atom. And these are related to energy, magnitude of angular momentum, or vice versa, magnitude of angular momentum, projection of angular momentum on the z-axis, and spin. So that's it. So we have to prepare even more definitions next. For a vector space, we all know what is meant by a homomorphism. A homomorphism is a linear mapping that preserves the linear structure of the vector space. So a homomorphism leaves linear combinations in the vector space invariant. The same can be defined, of course, for algebras as well. Now we have to include 2 additional axioms. So a homomorphism applied to an algebra product should be simply the product of the images of this homomorphism, and it should be compatible with involution as well. And then we talk about star homomorphism, when we are mapping elements of a C-star algebra onto elements in a different C-star algebra, from one algebra A to another algebra B. So this is a star homomorphism. Then we have the usual conventions that bijective star homomorphism is called a star isomorphism. If we are mapping not from one vector space into another one, or from one algebra into another one, but we remain within the same algebra, we are talking about endomorphisms, star endomorphisms, and if they are invertible, we talk about star automorphisms, which are bijective endomorphisms. Nothing new, just the same notions from linear algebra applied to the algebraic framework. Interestingly, and this is also not very new for you, that the automorphisms, the invertible star homomorphisms within the algebra, they have again a linear structure. So this is another vector space. Of course, if you consider the matrices, the quadratic matrices mapping vectors from one space into itself, the matrices also form a vector space. And this is the same here for C-star algebras. You call this one the automorphism group. So the automorphism group is simply the linear space of all the automorphisms mapping A to A, such that this phi is a star automorphism, an invertible endomorphism, and of course, similar as I can compute a matrix product in order to express the function composition of homomorphisms, I can take the composition product into account. With respect to this composition products, we have a group structure for these automorphisms. This is known as the automorphism group of the algebra. So now, two very important definitions. First of all, we can describe the action of any group. So this should be a set G and operation on this set G, such that G and this plus together form a group. And on the other hand, we look at the automorphism group of the C-star algebra. And then we describe the mapping from the group into the automorphism group. And this mapping is called a group representation if we have exactly this property that the group structure is being preserved. So the image of this group operation here should be reflected by taking the image of the element A of the group, the image of the element B of the group, and taking their composition product in the automorphism group. Then we talk about a group representation. And this is now the crucial notion in order to relate the abstract structure of C-star algebras with the concrete properties of pioneer quantum mechanics. Then we have to talk about algebra representation. So, and again, we consider a mapping pi, which should be a star homomorphism from an abstract C-star algebra into a concrete C-star algebra, namely into the set of bounded linear operators over Hilbert space. And we call this homomorphism, the star homomorphism, a representation of the algebra in the so-called representation space, which is underlying Hilbert space. And in that way, in that sense, we assign to any abstract elements of the algebra a representative phi of A, which is an operator acting on the Hilbert space. So, and here you see now phi of A applied to a state psi 1 should be a state psi 2, and we are able to reproduce or to rephrase all the concepts that we have developed so far during the discussion of pioneer quantum mechanics. This is now the missing link, so to say, to connect algebraic quantum theory to real quantum theory, so to say, in mathematical physics. This is all about algebra representations. Well, here's an example. Let us look at again at the qubit representation of this abstract Pauli algebra. So abstractly, the Pauli algebra was given by these elements of an algebra, but now we have to represent these elements by 2x2 matrices, and this is the result of the representation. And what is required in order to prove that we have really a representation is the following. We have to prove that this mapping, this star homomorphism, leaves the fundamental commutation relations invariant. And so, for example, what we have written down a few slides before was one of these commutators. If you remember, I hope this was the right choice. This is the one of the fundamental commutation relations in the Pauli algebra on a very abstract level, so to say, on the ontological level. But now, in order to prove that we indeed have a representation in terms of these matrices, we have to prove that The same commutation relation holds also for the Pauline matrices. And we can do this for just this example, probably as an exercise. So what do we have to do? We have to compute the commutator pi of Sx pi of Sy So, and what is this? Now, of course, we need the definition of the commutator. And we have to compute these matrix products here. So what is the result? This matrix product here gives 0 times 0. Times 0 plus 1 times, oh, sorry, that was wrong. Oh, was it? Ah, yeah. Was it wrong? So remember the rules for matrix multiplication, row times column vector. So 0 times 0 plus 1 times I is y. Then 0 times minus I, 1 times 0. 1 times 0, 0 times I. And 1 times minus I, 0 times 0 minus I. Then we have to subtract this result, 0 times 0 minus I times I1. 0 times 1 minus I times 0. I times 0, 0 times 1. And I times 1, 0, 0. Well, this is essentially the same metric. No, it's not the same. Minus. It's minus. But this is. Well, this is, yeah, of course. I wanted that, maybe a bit more exclusive. And I, this is I. Oh.
Minus 2i in the second.
Yeah, yeah, thank you. Minus 2i. And then you see our one half.
Equality is 1/4, and then circular.
Oh, sure. And this is exactly yeah, this is the representative matrix of Z. Yeah, so we have proven the invariance of the commutation relations, at least for the first example or for this example here. And therefore, we have proven to some extent that we indeed have a two-dimensional representation of the spin algebra. Interesting is also the representative of the Pauline operator, which is a multiple of the unit matrix. And you remember that multiples of the unit matrix or of the identity are in the trivial center and do not count as a classical property. I come back to this as well. So that essentially means that in this representation we do not have a classical property. Also, it appears to be. Okay. Well, here's another example, namely again the particle in the box. And we can also show that this is indeed a representation. So we had introduced the Heisenberg algebra by the identity, by the momentum, and by the position operator. And now we don't use matrices for representing these algebra elements, but we use derivatives and functions acting on wave functions, namely on square and integrable functions over the real line. And again, we have to prove that this is indeed a representation. Can simply do this for u and pi, which we know should be I times identity, if I'm right. And of course, now we have to prove again that the representative of Q and the representative of P are I times the representative I. Well, what do we have to do? We have to apply this to a wave function in order to make sense out of that. So let us make a slight modification. Apply this commutator to the wave function psi, and this should be I times E of I applied to the wave function psi of x. So, and now we can proceed. This should be x, and this should be minus I x. I could sub from x. That is x minus I x x minus plus I dx. I write it that way. We have to apply this to the wave function. So I x, the derivative of x plus e, and the derivative of this. This gives I psi plus x psi prime. Well, and then we have minus ix psi prime and plus ix psi prime. And you will see immediately this is nothing else than I psi x, which is I times the representative of the unit times psi of x. So we have proven the Heisenberg commutation relation and got a representation in this function space. Now we come to a representation of these field algebras. I have already mentioned this field algebra is generated by the polynomials in these two operators, and they are parameterized by the single particle states in the Hilbert space. the Hilbert space. We can choose this L square space, for example, in the Schrödinger picture, is an infinite dimensional vector space. And so this field algebra is actually being represented, so to say, in analogy to the Weil algebra, parameterized by an infinite dimensional state space. And what is the appropriate representation space for that? And it turns out that the representation space for such a field algebra is the so-called Fock space. And the Fock space, first it has a conventional definition that we namely take the single particle Hilbert space that we use here for the parameters of the field operators. And then we take this single particle Hilbert space to some tensor product powers. So that means essentially I write h to 2 is simply h times h, and then correspondingly h to, yeah, I say inductively n plus 1, h to n times h. This kind of tensor product power can be defined inductively here. So we take, again, this was, I think, related to his question before. So we take a single particle Hilbert space. We compute replicas of this by means of these tensor products here. And finally, we superimpose all these tensor product spaces of course, different dimensionality, which is formally carried out by this direct sum. So it's essentially the outer direct sum that we need. And this structure here is called the Fock space. And of course, we do this for an infinite number of replicas in order to account for the possibility that such a field could have an infinite number of degrees of freedom. But this definition is quite useful, particularly in applications, which I will show in one of the next slides. But it is very cumbersome for calculations in the framework of quantum field theory. And there, a different representation is much more advantageous. And this is a so-called occupation number representation. I write it down in that way. So let us consider the space n0, the set of non-negative integers, to the power of this Hilbert space. So what does this mean? I think this is a notation that is well known in computer science. Have you already seen this kind of notation? You do. You know what is the interpretation of n0 to the power of h, where h is this infinite dimensional Hilbert space. Great. As I said, it's a notation used commonly in computer science. It means the set of all the functions. So I write it down on the blackboard. Maybe I will start with another example. Let us consider a set A of some elements. A is a set of elements A, where just with the property that A is an element of A. Do you know this expression? That you know. This is nothing else than the power set of A. And formally, it means the set of all functions that bring A into the set of binary numbers. So every time we have a mapping of A into 0 and 1, we are in one of these elements here. And correspondingly, n 0 to h is the set of all functions bringing the single particle Hilbert space onto a number. And that means if we have one particle, we say that this particle is mapped onto 1. If we have two particles, we can say the particle in one of the states appears no, other way around. That the first particle appears in one of the states here, and the second particle appears in another one of these states. And so here's the solution of this puzzle. So first of all, we introduce the so-called vacuum state. Namely, again, here we have a representation of this element of the field algebra, and then we say the vacuum state should not contain any particles, and this vacuum state should be annihilated by the representative of this operator here. And then, now that was my point, we introduce these so-called occupation numbers. That means we have this is again this is a vector of this Fock space, namely taken as the set of functions from the Hilbert space into the non-negative integers. And all the time, so we are enumerating, this is the first state of the Hilbert space. The second state of the Hilbert space here is the end state of the Hilbert space. This is possible because we assume that the Hilbert space is separable, and therefore it has a countable basis. And we have a ground state, so we can really start with one particular basis, ground state here. And then we say, if we look at one particle, at a one particle state, which of course corresponds to the fact that the state is an element of the Hilbert state here, then we have exactly this representation here by means of occupation numbers. So and again, this operator here, this field operator, should be an annihilator, and that means the representative of this operator acting on this Fock space, on this occupation number representation, simply takes away this particle, this single particle in the nth state of the Hilbert space, and producing the vacuum state. Then, by contrast, and this can be inductively generalized, of course, we say that now this adjoint operator here, which is not an annihilator, but a creator, represented as an operator on this Fock space, applied to the vacuum, creates exactly one particle in the nth state, in the nth state of the Hilbert space. So this is the occupation number representation. Well, for that I have an example, and I don't know, do I have still time?
You still have 15 minutes.
15 minutes. Okay, then let us try to understand this example. And this is really now an example related to our own research that we have essentially conducted in Cottbus over the last years. And this is now really an application of this formalism in artificial intelligence. It is generally called vector symbolic architectures. This concept has been introduced by Ross Gaylor a couple of years ago, and since then it became quite familiar to talk about vector symbolic architectures. Sometimes people also use to speak about hyperdimensional computing. And here's the essence of this idea. So in artificial intelligence, we are looking at many different kinds of symbolic processing. And one of these different examples for symbolic processing is, of course, language processing. And in language processing, I just give a sketch here of a possible language processor, so to say, an artificial intelligence that should understand or that should process a sentence like the mouse ate cheese. So let us consider an artificial intelligence processing the mouse 8 keys. And in linguistics, sentences are described by hierarchical symbolic structures, namely phrase structure trees. And these phrase structure trees can be written down in such a way that at a particular point in time during such a process, the agent only has prepared a preliminary representation of the sentence. And what is shown here is basically a so-called left corner processor or parser that is able to generate such a structure describing the sentence incrementally. And so the background for this are formal grammars, so contextual grammars in this particular example. And here you see we assume that the system has already processed the first word of the sentence, namely the. And the has been identified as an article. In grammar theory, we are using particular symbols to characterize this. This is just the symbol here. And then one knows that the C or the article should be one part in the so-called noun phrase. This is the NP here. And from this noun phrase, we predict now the next incoming word should be a noun. This is the basic idea. So here you see this symbol N in brackets that should be the predicted entry. And now the agent hears or recognizes the next word of the sentence, mouse. And this mouse leads to a revision of the structure being processed. Namely, first of all, the mouse is, of course, a noun. So the expected noun has been confirmed. And therefore, the mouse can be joined with the structural representation already processed in that way that we can attach the mouse here to the noun node in the tree. And then also this NP has been confirmed. And now the processor makes another prediction, namely we should expect a sentence, and the sentence should next have a predicate. And of course, when I say the mouse ate cheese, one would next expect the verb ate. And so this is a very abstract description of such a symbolic process. Of course, this is standard in language technology and, of course, in computational linguistics. But how can we relate such a representation here, such a structural representation, to any kind of algebraic treatment? That's the question. I don't know whether we can do this today or whether we should continue tomorrow. So let me start with this. The crucial notion for that, I'm not sure whether here is the crucial notion. What we need is so-called term algebras. And at that point, I would already like to make this claim that when we are talking about explained or explainable artificial intelligence, so not training deep neural networks where nobody knows what is going on somewhere in the deep layers, but when we at every instance of time when we want to interpret the state of the system, we need something like this. And this would be really my, so to say, my claim that explainable artificial intelligence should be the representation theory of term algebras. Okay, let me just start with the introduction, and probably I will stick with this example. So first of all, and unfortunately I don't have prepared the slides because I wasn't sure whether I will still have the time for that, but let me try. So what we define is a so-called signature. And now, again, I'm talking about symbolic processes, so to say, about discrete mathematics and not about algebraic quantum theory at all. But eventually, we will see that there is a close connection. And I hope I can convince you about this connection. So what is a signature? We start with a finite set. And this set should contain all these different symbols that we need in order to make such a structural representation. So the set should contain the symbol S, which is interpreted as we have a sentence. And it should include the NP, which is literally a noun phrase, and it should contain a verb phrase, which is the predicate of a sentence. It should contain an article and a noun and predicted categories such as a predicted noun and a predicted verbal phrase. And of course, all the individual words like the and mouse and ape and so on and so forth. So in computer science, you often say this is an alphabet. This is a finite set of some symbols. And this is our starting point. Next, we introduce a function of S into the non-negative integers. And how do we do this? For example, we say S of S is true. And S of the, for example, is 0. And for sigma of the is 1. Can you recognize the relation to this to the tree structure I have drawn there? No, it's not a level. The point is, S has 2 branches. D has 1 branch, and Z has no branch at all. So, if there are no branches, which means in the corresponding grammar formalism, we have terminal symbols, we speak about constants. If we have only 1 branch, we speak about a unary symbol. And if we have 2 branches, we speak about a binary symbol. And this mapping here, this is called an arity function. Assigning the number of possible branches to all these elements of the alphabet. And by this arity function, these symbols become function symbols. What we can write down now means here at the very beginning, we have NP with arity 2. So NP takes 2 arguments, namely D and the predicted N. And now we can iterate this process. For example, D is a unary function, which takes argument the. So, and this can be inductively generalized. And then we say all the constants are terms. If something is a term, then also, so if I write it down more precisely, so all the constants are terms, definition. If T1 and T1 and T2 are terms, then T of T1, T2 is a term provided T is of arity 2. And of course, if the arity of T is only 1, then only T of T1 would be a term, and so on and so on. So, and this defines the term algebra at a very abstract level. And interestingly, if you are familiar with Mathematica, are you? Do you use Mathematica for your research? And so take a closer look at the data structures in Mathematica, and you will realize every Mathematica expression is a term of such a term algebra. That's it. I think we should close today, and let me elaborate this interesting, amazing example tomorrow. You're welcome.
Thank you, Peter.
You are welcome.
Questions? Okay, thank you.
Yeah. See you tomorrow.